Okay, we're ready to go ahead and solve this problem to find the probability that the average height of a random sample of 12 flowers is greater than 17.5 inches. So one method would be to convert this to a problem about z-scores. We need to convert this number 17.5 inches to a z-score using this formula z equals x bar minus mu over sigma divided by the square root of n. So in this example, the x bar is 17.5, the mu is 15.5, the sigma is 2.2, and the n is 12. So when I put that into my calculator, parenthesis 17.5 minus 15.5, close parentheses, divided by parenthesis 2.2 divided by the square root of 12. Remember, I said you do need parentheses around both the numerator and the denominator of this expression. So that came up as 3.149 something, and if I round that to two places after the decimal point, the nearest hundredth is 3.15. Now we've got to look for that on the table, table E. Look up where z is 3.15, and the number on the table is 0.9992. Then because we want the probability of z being greater than 3.15, it's a greater than kind of a question, we need to subtract that number from 1. Our final answer is 1 minus the number on the table. 1 minus 0.9992, which is 0.0008. Now that's a really small probability. It's 0.08. So it's a little less than 1/10 of 1%. If you remember last time, we found the probability that a flower would be more than 17.5 inches high. It wasn't a huge probability, but it was something that could happen. But here we've got the probability that the 12 flowers in your sample have an average height of greater than 17.5. That is very unlikely to happen. In order for that to happen, for those 12 flowers to have an average height of greater than 17.5, either they'd all have to be taller than 17.5, or if some of them weren't, the others would have to be enough taller than 17.5 to sort of make up the difference. So that's something that's not very likely to happen for a whole group of flowers to have a sample mean that is that high above the population mean. Now let's talk about some of the other ways we could do this. If you have a graphing calculator, you could just use the normal CDF function on the calculator. So remember, go to the distributions menu, select the second thing on the list, normal CDF with a C. And in this example, we were going from 17.5 all the way up. Greater than 17.5 means starting at 17.5 and going on up to infinity. So my lower limit is 17.5, and my upper limit, I'm just going to put in something really big like 9999. For mu, I'm putting in 15.5. And for sigma, I am putting in 2.2 divided by the square root of 12. That's the sigma, the standard deviation of the x bars. So instead of just the 2.2 for sigma, we're putting in 2.2 divided by the square root of 12. Now we paste that in, hit enter, And notice it gave us the answer in scientific notation. That's what the E minus 4 is. So if I shift the decimal point 4 places to the left, it does look like 0.0008. If we wanted to use the Desmos app, so go to the Functions menu, select Dist for distributions, select Normal Dist, and now in what comes up, I need to put in the two numbers for the mean and the standard deviation. So the mean was 15.5, comma, and then the standard deviation I'm going to put in as 2.2 divided by the square root of 12. So we're working with a normal distribution with a mean of 15.5 and a standard deviation of 2.2 divided by the square root of 12, which is what it is for the sample means, the x bars. Now I check the box next to find cumulative probability. My min, my starting point or lower number is 17.5, and my max, my upper number is infinity, so I'll just leave it like that, and the number that shows up here is 0.0008. And if you wanted to use this online normal probability calculator, you'd put in, for mean, you'd put in 15.5, and for the standard deviation, you'd probably have to calculate that yourself. Use your own calculator to work out what 2.2 divided by the square root of 12 actually is. So it's about 0.635. And then we want the probability of x being greater than 17.5. So select that, put in the number 17.5, hit calculate, and it does show up in red there as 0.0008. So let's go on and look at another example. Suppose there's some test, like an IQ test, for which the scores are normally distributed, and suppose the mean is 100 and the standard deviation is 15. Look familiar? Same setup as in some of the examples from the last section. But this time we have a group of 25 people taking the test. If that happens, what's the probability that the average, that is the mean, of their scores is greater than 105? So notice what we want in probability notation. This would be the P of x bar being greater than 105. The probability of the sample mean, the average for that group of 25 people, to be greater than 105. So, however we do it, if we calculate the z-score, we got to use 15 divided by the square root of 25. 25 is our n. If we use the calculator app or something like that, we put 15 divided by the square root of 25 in for the sigma, the standard deviation. The z is 1.67. If we look it up on the table, we get 1 minus 0.9525, which is 0.0475 or 4.75%. That should also match what you do if you use the calculator function. So that's the answer, 0.0475. And one more example. Assume that the mean systolic blood pressure of normal adults is 120 millimeters of mercury, so that's just the unit that blood pressure is measured in, and the standard deviation is 5.6. Assume the variable is normally distributed. Now this is a two-parter. In part A, it says, if an individual is selected, find the probability that the individual's blood pressure will be between 120 and 121.8 millimeters of mercury. And then in part B, if a sample of 30 adults is randomly selected, find the probability that the sample mean for that group of 30 will be between 120 and 121.8 millimeters of mercury. So I've underlined what it is they're asking us to find in each part. In part A, we're supposed to find P of, or the probability of X, our random variable being just an individual's blood pressure. We want the probability of X being between 120 and 121.8. In part B, we want the probability of X bar being between 120 and 121.8. And our sigma, our standard deviation for those X bars, would be the individual standard deviation, 5.6, divided by the square root of n being 30. So I'm going to do this on the graphing calculator. For part A, I'm going to ask it for normal CDF, where the lower number is 120, the upper number is 121.8, the mean, the mu, is 120, and the sigma, the standard deviation in part A, is just 5.6. So the answer it gives us for part A is 0.126057, about 0.1261. If you did it using the table, you'd get something really close to that, maybe not exactly the same. Now for part B, go back to the distributions menu, select normal CDF. We still have a lower of 120, an upper of 121.8, a mean of 120, but now the standard deviation is 5.6 divided by the square root of 30. And now the answer it gives me is 0.4608. So it's 0.1261 for the answer to part A, the probability that an individual's blood pressure will be between 120 and 121.8. And the answer is 0.4608 for part B, the probability that for the whole group, their average blood pressure is between 120 and 121.8. Now, before I leave you in this section, one final question. How do we know what sigma and mu are? I've just been telling you in all these examples, the mean is blah, 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 and the standard deviation is blah, blah, blah. But how do I know? Like in the question about the flowers, how do I know that the mean is 15.5 inches and the standard deviation is 2.2 inches? Well, it's because I said so. I made up the example, I made up the meadow, and so I just told you, I said so, this is what those numbers are. But if this had been a real-world example, based on an actual meadow full of flowers somewhere in the real world, then the only way you could know for sure exactly what these numbers are is by going out and measuring all the flowers in the meadow. So this represents what you would get if you could go out and measure every single flower in the whole meadow and take all of their heights, add them all together, and divide by how many there are. That's the population mean. And so that's the only way of knowing exactly what that is, but you can often get a pretty good idea and come pretty close just by taking a sample of flowers. And that sort of leads us into what we're going to be talking about in the next chapter. We'll be talking about the relationship between populations and samples. And today we talked about, if you know what the population mean is, what can you say about sample means? What's the probability that the sample mean is within a certain range? Next time we'll kind of do the reverse of that. If you know what your sample mean is, you've gone out and gathered a sample, and you figured out what's going on with your sample, based on that, what can you say about the population? How can you estimate the population mean? How close can you come, and how sure can you be that you are that close? So that's kind of a preview of, or a foreshadowing of what's coming up in Chapter 7.